All right. Good afternoon, everyone. Glad to see some of you guys here. Sorry, the link. I just forgot to even create the link until about 5 minutes ago. But anyway, sorry about that, guys. And Adam, good to see you here as always. And good to see that you didn't see or you weren't prepared for my sneaky bishop. So sorry about that. And hopefully no hard feelings on that one. All right. How's it going, Jeremiah? All right, so today we're going to be going through the practice problems. If you haven't done the review yet, you might as well just stop this video and come back later, okay? No point in watching me go through these until you've tried them yourself, okay? That's the whole point. So if you want to actually do well in the test, make sure you do the review, go through the practice problems, and are able to solve them, right? Watching somebody do them, if you've never tried them, isn't necessarily going to be nearly as effective as trying them yourself first, okay? Yeah, my bishop. Bishops don't look as scary, right? You think if that was a queen in front, you would be like, oh, I got to protect myself. But because it was a bishop, you're like, oh, hey, it doesn't matter, right? And then you realize, oh, wait, my king has nowhere to move. So sorry about that, but not actually sorry. I thought it was kind of cool. But anyway, on to the physics. You'll probably win the second game, I'm sure, Adam. All right. Here we are. We have two charged objects, 2.5 centimeters apart. And we're going to have to worry in all of this, we're going to have to worry about units. As I can see right now, we've got centimeters here. We've got micro here, and so that's going to be annoying, these prefixes for all of our units, okay? So we got two charged particles, and so our value for R right now, let's just go ahead and write it down. So it's 2.5 centimeters, but what is that in meters, right? Centimeters is 10 to the minus 2, so we need to move that decimal point 2 spots to the left, right? So that's going to be 0.025 meters. Go ahead and put that in meters right away. One has a charge of, so this is going to be, it doesn't really matter which one's which at this point in time. So Q1 has a charge of negative 5.7 times 10 to the minus 6. So that's micro, which is 10 to the minus 6 coulombs. And the other one, Q2, has a charge of a positive 14.2 times 10 to the minus 6 coulombs, okay? And so it says calculate the magnitude and direction of the electric force on the first object. And it doesn't really matter whether it's the first object or the second object. We do remember Newton's third law, and that is that these two forces are going to be equal in magnitude and opposite in direction. So it doesn't matter whether it's asking you about the first object, the force in the first object or the force on the second object. Okay, so I'm going to go ahead and say the direction first. All right, the direction is going to be, they're attractive, right? And how do I know they're attractive? Because this is negative and that's positive, right? Positive and negative charges attract. So this is going to be toward the second, I don't know why this is shaking, object. Okay, so toward the second object, and we don't know exactly where they are in space, so it doesn't really matter. We just say, okay, this is going to be a force that's toward the second object. Now that we've got that worked out, we can go ahead and calculate the magnitude. Okay, so that's the direction right away. And sometimes you might even want to answer that at the very beginning, because after you've done all the math, you might forget about it. But it doesn't matter. You can do the direction at the end too. All right, so here we go. Our force for any kind of charged particle, so our electrostatic force or electric force, is going to be equal to the Coulomb's constant Q1, Q2 over R squared. And, oh, I know what's going on. That thing's touching. Okay, sorry about that. All right. So, yep, there we go. All right. So don't forget the square here, and that's a big mistake that people make a lot of times after they get through all this stuff. They write the square down and then they forget to actually square it at the end of the day. So don't forget about that. we don't need to rearrange anything because we're calculating the force. So let's just plug in some numbers. Our Kc value is, that's your 8.99 times 10 to the 9th newtons meters squared per coulomb squared. And then it's just all these numbers that you have here. So it's your Q1, that's going to be our negative, and we're not going to really worry about negatives and positives here. Once we got the direction, that's all they're valuable for. 5.7 times 10 to the minus 6 coulombs. Q2, 14.2 times 10 to the minus 6 coulombs. All divided by, oops, how did this change in, all divided by what? We have r squared, so it's 0.025 meters squared. Okay, and so just make sure our units work, right? So we have newtons on the top, and then meters squared over meter squared cancels, coulomb squared on the bottom, and coulomb squared on the top cancels. So we're going to be left with newtons for our units. All right, so now we can just plug in some numbers. And I feel like these initial problems, the first couple problems, are actually the more challenging problems that you have. So I think we kind of started off on the more challenging stuff, but maybe different people find different things challenging. Who knows? All right, 8.99 E9 times 5.7, and I'm not even going to worry about that negative sign right now. All right, that's just got to do with the direction. That's it. 5.7 E negative 6 times 14.2 E negative 6. And you can go ahead and get your answer here and then do the next step. I'll just go ahead and put it all in one line. Divided by 0.025 squared. And that should be good. So that's a pretty big number, 1,164. 1,164 newtons. So yeah, so that's what we got here. And does it make sense? I think that makes sense. So this is, yep, that looks about right. All right, any questions on number 1 here? So be careful with the units. If any problems arose, it's probably got to do with those prefixes for the units. But that's number 1. Number 2, I had a couple of people that were wondering, well, what's the deal with this alpha particle and all that kind of stuff? Should we always convert centimeters to meters? Yes, pretty much always. There are a few cases where you don't need to convert centimeters to meters. And I think that when we were doing fluids, I remember that we didn't need to. So essentially, if at the end your centimeters are part of your units, okay, so for example, I think we had, when we were talking about like the fluid, the flow rate of different liquids and stuff, we were talking about something like centimeters per second and stuff like that. And that's fine if you have centimeters there and centimeters there in your units for your answer. However, when we're dealing with SI units, right, your metric units, and you need to have newtons here, then you need everything to cancel out. So we have meters squared here, so we need to get rid of those meters. So in general, it's good habit to always convert your centimeters to meters. And it's even trickier when it comes to mass, right? So for mass, what are the units that you should use for mass, right? They're actually not, you might think it's going to be grams, but it's not. The units, the SI units for mass are not grams. They are, in fact, kilograms. Okay, so we need to convert your distance always to meters, right? Charge to coulombs, force is newtons, and mass is kilograms. So whenever we're getting the electric force, we can take the absolute value of the answer, since the sign, since the positive negative is just exactly. The positive negative is just used for the direction. So it's to tell you, are they repelling or attracting? And that's it. I'm not going to give you on the test any situation where you have 3 different charged particles, okay? Which will complicate things. I think you had something like that on your homework. But just like the review, we're not going to have any situation where there's more than 2 charged particles. And so in that case, you might need to be a little bit more aware in terms of positive and negative. But in this case, we can just literally just take the absolute value and think, okay, is this attracting or repelling? It's positive and negative, so it's attracting, and that's it. Yeah, and that's fine. I'm not going to, if you have this as negative, I'm not going to really worry about it, okay? But again, remember that the negative sign means that it's going toward the other particle, okay? And that's it. It's an attractive force rather than a repulsive force. So just remember what they mean. And I'm not going to worry too much about your charges, your positives and negatives there, okay? So, hey Alex, how's it going? And Natanya, this is physics class, but if you have a question, I can talk to you at the end, but we just started, so I've got a bunch of physics problems to go through, okay? So you're welcome to come back on later, or you're welcome to listen to physics. It's whatever you want to do. It's up to you. All right, so back on here. So number 2, we have an alpha particle, and like I was mentioning before, oh, you just want to say hi? Of course, because all the stuff we're doing in chemistry is so easy, so you guys don't need any help, actually. All right, cool. So hi. All right, so back on here, number 2, an alpha particle, right? And so I don't give you guys a whole lot of information about the alpha particle, but I do say, okay, it's 2 protons and 2 neutrons, and so you might want to look up what is the mass of this thing. It's going to come in handy at some point in time, so you can just look it up. You could calculate what it is by adding the masses of 2 neutrons and 2 protons, but your answer won't be exactly correct because when you put them together, the mass actually decreases some. And so it's best, literally in this case, this is one of those cases where it's literally best just to Google it. And you find the best answer actually on Wikipedia, which is going to give you, and I'm just going to round this to 4 sig figs, but the mass of this is 6.645 times 10 to the minus 27 kilograms. Now again, we said we want our units for the mass in kilograms, not grams, and definitely not anything like AMU, because that's how your SI units are going to work. Okay, so that's your mass, your charge, and so your charge for this thing is going to be equal to that. You might want to calculate, or you could look that up too. I didn't look it up in this case. It's going to be twice the charge because you have 2 protons. It's going to be twice the charge of 1 proton, and the charge of 1 proton is exactly the same as the charge of an electron, only it's positive, and that's going to be 1.602 times 10 to the minus 19 coulombs. Okay, so those are your numbers to start off. So it's in an upward electric field, and that's going to be your electric field strength, which is equal to 3.25 times 10 to the third newtons per coulomb. Okay, so it looks pretty scary, but at this point in time, it's not such a bad calculation, right? Your force is simply going to be what? It's simply going to be your electric field times the charge of your particle in there, and that's it, okay? So let's go ahead and just, I don't even need to write this out, right? Because you have it right here. So it's just going to be your electric field strength times the charge of your particle here, your alpha particle. And so let's just go ahead and do the math. Okay, that's going to be 3.25, and that's, notice the units here, newtons per coulomb, right? And then we're going to be multiplying it by the charge here of 2 times 2 times 1.602 to the negative 19th. And so we're expecting a fairly small force, which makes a lot of sense because this is just one small particle. So 1.04 times 10 to the negative 18, and the units are going to be in newtons, right? So this is newtons per coulomb and times coulombs, so the coulombs over coulombs cancel, and we're left with just simply 1.04 times 10 to the negative 18 newtons. So that's the force. Now, I might do this on the test, so just be aware. Now it says also the acceleration. So we're not just calculating force, but also acceleration. So we can go back to what we learned way, way back at the beginning, the first semester. And don't forget this, because this is one of those, very, very important equations, and that's F equals ma. Newton's, and which law of Newton is this? Do you guys remember? One of Newton's laws. We've already talked about Newton's third law. Remember, Newton's third law was that these forces are equal in magnitude but opposite in direction. So you have those two charged particles, forces are equal but opposite. And F equals ma, I don't know. I don't even know if anybody from my physics class is still on here, because I told everybody to leave if they haven't finished the review yet, which means they may not have finished. All right, Adam's still here. All right, Jeremiah and Adam. Yes, second law. Very good, very good, very good. That is the second law of motion. You're right. So once we know that, we can go ahead and divide both sides by the math. So your acceleration is going to be force over the mass. And so we have the force of 1.04 times 10 to the negative 18 newtons. Divide them by the mass. We add the mass in kilograms. This is going to be an insanely large acceleration, right? We have 6.645 times 10 to the negative 27 kilograms, okay? And we can see that it's going to be a ridiculously fast acceleration because we have 10 to the negative 27th on the bottom. Let's go ahead and put it in our calculator, okay? So we have this. You got something different for force. You got 1.04 times 10 to the minus. Did I mess up? Negative 15th. I got negative 18th. You got negative, you're going to have to go upstairs. You got 10 to the negative 15th. Did you do it in grams? No, wait, what do we? We have coulombs. Hold on just a second. Okay, 10 to the, sorry. You got 10 to the negative 19th here for charge times force. Did I forget to put that negative, that 3 in there? I think you might be right. Let's go ahead and try that out again. 3.25. I may have forgotten that 3. That may be the problem. 3.25 times 10 to the third times 2 times, yeah, I think I did, 1.602 e negative 19. Okay, you're right. That's negative 15th. Thank you, guys. Nice work. Nice work. All right, exactly right. So this is 1.04 times 10 to the negative 15th. 1.04 times 10 to the negative 15th newtons. Exactly right, which is going to make this even larger. So that's the force divided by 6.645 to the negative 27th. And there we go. That's going to be 1.57 times 10 to the 11th. That is a huge number. 1.57 times 10 to the 11th. And the units are what? What are the units for acceleration? So newtons per kilogram. Remember, what's a newton? A newton is a kilogram meters per second squared. So you're going to end up with meters per second squared, which makes sense because this is acceleration. That's an insanely large acceleration. And that's all I can say about that. So 1.57 times 10 to the 11th meters per second squared. Yeah, we're talking about particles here. So particles can move very, very fast. And this is not, although we say it's an extremely large acceleration, it's not unheard of when you think about things like particle accelerators and stuff like that. So you can definitely achieve things like this and even greater in particle accelerators like the cyclotron and other things like that. All right. So will there be something like this on the test, just directly dealing with a book concept? Maybe. Yeah, I wouldn't be surprised to find something like this in the test, but then again, maybe not. I don't know. I still got to write the test. So, yeah, maybe. We'll see. I wouldn't be surprised. All right. You would you would either have the mass provided, or you could do exactly what you did for this problem and literally just look it up. I would probably provide you with the mass, I would think, because I wouldn't want you guys to waste time and then run into, let's say, bad information on the internet. So yeah, I would, if I gave you something like this, I would provide you with the mass. Good call. Yeah, I would provide you with that stuff. Yep. Okay. All right, number 3. We got a parallel plate capacitor, so we're dealing with capacitance now. And the capacitance, so your capacitance here is going to be equal to 13, and I think we can leave it as microfarads. Let's see what happens. We have a potential difference, and so that's going to be your V, or your delta V is going to be 9.0 volts. And we want to figure out, okay, what is the charge on both plates, and we want to know what's the potential energy that's stored by the capacitor. So this is kind of similar to some of the questions you guys had on capacitance in your homework. So let's go ahead and do that. So we have the equation for capacitance, which is the charge. Remember, this here is the charge on both plates. Both plates have an equal charge over delta V, and we know C and we know delta V, but we don't know Q. So we're going to go ahead and multiply both sides of the equation by delta V. So Q equals C delta V, which is going to be 13 microfarads times 9 volts, which is going to be 13 times 9, or 117. 117. And this is a case where you can just leave this as micro. So I'm going to keep the micro here because we're multiplying. When you divide by something that's micro, so if micro was down in the denominator, it could mess you up. But as long as we're just multiplying things, no big deal. So it's micro what? We're talking about charge here. Charge is going to be in coulombs. So that's going to be 117 micro coulombs. Okay? So, or a farad times the voltage is going to be a coulomb. Now you have your equation for potential energy. You have a couple different equations. We can just go ahead and use the equation that is as follows. So potential energy is 1/2 Q delta V for a capacitor. So that's going to be 1/2 your 117 microcoulombs times your 9 volts, and that's it. So 117 times 9 divided by 2 to get us 520. We'll just round it up. I mean, well, technically we really only have 3 significant figures here, so let's just make this 530. 530, and the units are going to be for potential energy, or any kind of energy, are going to be joules. But this is microcoulombs, and so we're expecting this is going to be microjoules. And if you got it into, let's say, something, you want to put it in joules yourself, this is going to be times 10 to the minus 6, and then that's going to be, what's that going to work out to be? That's going to be 5.3 times 10 to the minus 4 joules. So that'll, if you want to put it in scientific notation, you can do that. Okay. So not a very big amount of energy there. All right, so that's it for the first page, guys. Any questions? I'm glad you guys here, so you can check my work if I make a mistake. And so that's nice. Hopefully you guys have done your work too, and we can all compare answers if we get different answers here. But let's go ahead and move on. We have... All right, how much charge passes through a wire in 5 minutes when 25 milliamps of current is flowing through the wire? Well, multiple choice. I'm pretty sure I'm going to make this all free response. I can't really think up of any good multiple choice question. So this is going to be an all free response test. It's going to be really similar to this review. I'm thinking maybe more towards, probably it's going to be 6 questions. And I think 7 questions is a little bit too long. So it'll probably be like 6 questions, all free response. Just like this, and only a little tiny bit shorter, 6 questions rather than 7. I think that's kind of reasonable, something like that. And I don't know which one of these types of questions I'll take off, or they might all kind of change form a little bit. So don't expect it to be exactly like this. All right, so how much charge passes through a wire? Well, when we're talking about charge, so through a wire in 5 minutes, that's going to be your time. It's going to be 5 minutes, but of course, anytime we're dealing with time, it probably should be in seconds. So you're going to take your 5 times 60, so that's going to be 300 seconds. So that's what we're thinking right away. You have a current, and so your current is 25 milliamps, and you can use 25 milliamps, or you can use 25 times 10 to the minus 3 amps. That's probably going to work out best, because when we multiply 325, you're going to end up with a fairly larger number. So let's take away the milli there. So when 25 milliamps of current is flowing through the wire, well, what does that mean? So your current is your charge that flows in a certain amount of time. So your charge, we're trying to figure out charge, right? How much charge? So that's going to be your Q, which you're trying to solve for. We just multiply both sides by T, so that gets us Q equals I T. I is 25 times 10 to the minus 3 amps. Your time is 300 seconds. Let's go ahead and do this. So 25 e negative 3 times 300 gets us 7.5. That's nice. 7.5. And so what's that going to be? So amps times seconds gives us a charge, which is in coulombs. So make sure you go back and think, okay, well, what is the units here for charge? Please, guys, remember to put your units down. Such an easy way to lose points, or such an easy way to get points. So just write those units down. Think about what you're solving for. If its charge is going to be in coulombs and all that kind of stuff, okay? So in this case, it's coulombs, and notice that the milli went away because it was essentially 25 times 300. It's going to give you a fairly large number, 7,500, and so we just take away the milli that way. So 7.5 coulombs. All right, so number 5, that's a fairly large charge, 3,300 coulombs. 3,300 coulombs. It passed through an electric heater in 1 minute. So once again, your time is 1 minute or 60 seconds. If the heater has a resistance, so we get resistance is 7 ohms. We're going to calculate now the current, and we want to calculate the potential difference, or the voltage. Okay, so we got 2 things that we need to do. And probably, let's see, the first thing to do is probably to calculate I, right? And so we already have the equation up there. I equals Q over T. We can do that right away, right? Because we have Q, we have T, so we can calculate I. So that's going to give us 3,300 coulombs per 60 seconds is going to be, I think that's going to work out nicely. 3,300 divided by 60. Yeah, 55. 55. And remember, coulomb per second is an amp. So that's 55 amps of current. 55 amps of current. So calculate the current and the potential difference. Well, how do we get the potential difference? We have the resistance right there. And we know that V equals IR, Ohm's law. And if we want the potential difference, well, we don't even need to rearrange that equation either. So this is 2 things where we've got the direct equation we can just plug right in. I is 55 amps, and R is 7 ohms. So we just take our 55 times 7, gets us 385 volts. 385 volts. So that's a fairly large voltage, but it is possible. So this is not going to be something you can just plug into your outlet. But, one of those really big industrial looking plugs, might sometimes be a high voltage, like around 400 volts or so. So yeah, so this is possible, but it's not going to be your standard voltage at home. 385 volts. Okay, and you can even calculate, if you wanted to, you could calculate the power here. It doesn't ask us, but we can do it anyway, right? So your power is IV, and that's going to be simply your 55 amps times 385 volts. So we can see that in this case, it's basically amps times the resistance to get you your power there. Okay, so this is going to be 385 times watts times your 55, which is 21,000. That's an incredibly powerful heater. So 21,000. We'll just round that off to 200 watts. So that's a fairly powerful heater. Okay. But of course, you didn't need to do that. Next up, we're going to calculate power down here somewhere. So we have a small robot, has a resistance of 14.5 milliamps. That's messed up. I made a mistake here. That's a resistance is not milliamps. So I don't know how you guys did this one. Calculate the current and power. So this is totally messed up. You could think of this as two different ways. You could think of this as, because I messed up when I wrote this, I was like struggling to do this like at the last minute. So sorry guys, I have to confess to a little bit of procrastination here. Because I set this up wrong, you can either take this as the current or you could take this as the resistance. So let's just suppose I intended it to be the resistance. So let's go ahead and do it that way first. So we'll say, okay, resistance is going to be 14.5 milliohms. Okay. Yeah. It should have been, 14.5. Yeah, milliohms is way too small. So 14.5 ohms, or maybe you could say it's got a current of 14.5 milliamps. So we can take it either way. Let's just go ahead and see what it's going to look like. And, whatever route you took, let's see what happens. Okay. So that, no big deal if you interpret this one way or another. And if you interpret this as 14.5 milliohms, then you're going to get another answer, which is going to be off by 1,000. But let's see what it is. So it's going to use 4.5 volts, and that should be a point. I don't know what happened here. All right, so 4.5 volts, although I think they use commas somewhere in the world. So that's voltage of 4.5 volts. 4.5 volts. So let's first calculate in this case, let's calculate the current. So V equals IR. So I equals V over R, right? So divide both sides by R, you get I equals V over R, which is 4.5 volts divided by 14.5 ohms. Oops. Sorry. 4.5 divided by 14.5 gives us 0.31 amps. And if you interpret this as milliamps, you're going to get a super large number. You get 310 amps. Or sorry, if you interpret this as milliohms, you're going to get 310 amps here as your answer, which is fairly large. So, I mean, it would be, I suppose, possible for a very large robot, but this is a small robot. So, yeah. Okay, so 0.31 amps. And that's fine. And it also says calculate the power. So power is IV. So that's going to be your 0.31 amps times 4.5 volts. And let's do that. Times 4.5. 1.4. Let's just say 1.4 1.4 watts, which is very reasonable. Okay, 1.4 watts, very reasonable for a small robot. So that's one way. What if we interpreted this as your current, because that's current, right? Milliamps is current. In that case, you have to calculate the resistance, and we can go ahead and do that. And so your V equals IR. So your resistance is going to be V over I, which is 4.5 volts divided by 14.5 times 10 to the minus 3 amps. And this is going to get us what? 4.5 divided by 14.5 to the negative 3 is going to be 310 ohms. Okay? 310 ohms. And then your power in this case is simply going to be IV. So that's going to be 14.5 milliamps times 4.5 volts. So it's going to be a small, fairly small, so 14.5 times 4.5, which is 62 milli. Now we didn't get rid of the milli, so it's 62 milliwatts. Okay, so different ways that you could have interpreted. Either way, if I made a mistake like that, you can interpret it either way, and that's fine. Okay, so 1.4 watt robot makes a lot of sense. 62 milliwatts is kind of small for a whole robot. So I think this should have been interpreted most likely as 14.5 ohms, and that would make a lot of sense in that case. So this is probably the best way to interpret it, but if you interpret it this way, it's also okay. Okay. Last problem, and then we're all done. Last problem of the year. Crazy. Okay, we have and these are like real reasonable numbers here. So we have 13 watt light bulb. So this is going to be our power. 13 watts is plugged into a standard outlet, right? And so so this is a fairly normal wattage. I think it's like equal to it's either a 75 or a 100 watt. I think this might even be a 100 watt replacement. 100 watt replacement LED. Because I think they're almost 10 times as efficient. They're not quite 10 times as efficient, but almost 10 times as efficient as the incandescent light bulbs. And so, yeah, I know that I have some of these 13 watt light bulbs myself, and they're fairly bright when they're the LED ones. So I'm pretty sure that this is a 100 watt replacement LED. And so when we say 100 watt replacement, those LED light bulbs don't actually use 100 watts. They only use, let's say, 13 watts or whatever actually what it's rated for. And they're as bright, or should be as bright, as an ordinary incandescent 100 watt light bulb. But they lose a whole lot less energy due to heat. So that's the power. Your voltage is 120 volts. What's the resistance? We could go ahead and calculate what the current is and then calculate the resistance, or we could do a substitution. So either way is going to work, right? You have your power is IV, and you have V equals IR, and you want to solve for, we're calculating the resistance, right? We're calculating what is the resistance, okay? In this equation, we don't have R, and we also, in this whole problem, we don't know what I is. Now, like I said, you could calculate I first, but I'm going to go ahead and go around that by just saying, okay, well, I know V equals IR, so I know I equals V over R. So I'm going to go ahead and plug that into this equation. So that's going to give me power is I, which is V over R, times V. So P equals IR. And that's going to get me, your power is V squared over R. And because we want to solve for the resistance, I can just flip P and R, right? I'll do that stepwise. That's going to multiply both sides by R, gets me P R equals V squared. or divide both sides by P, that's going to get me R equals V squared over P, which is 120 volts squared over 13 watts. Running out of space there. 120 squared divided by 13 is, that's a pretty significant resistance, but that's going to be a real number. Let's just give it two significant figures because that's pretty much all we have here. Both that 13 and the 120 really only have two significant figures. So this 1,100. 1,100 ohms, which is perfectly reasonable and correct. 1,100 ohms. Now, would a 100 watt light bulb have more or less resistance than that? And we can think about this one of two ways. We can think about this by simply looking at this equation. That's probably the easiest way to do this. The easiest way is going to be to look at this equation and say, okay, if I now increase this power, what's it going to do to the resistance? Well, increasing the denominator here is going to decrease the resistance here. So the answer is that 100 watts light bulb has less resistance. Okay? But we didn't need to do that. The other way to think about this is, well, okay, if you have just compare two different things that have different wattage, you plug them into the same exact same exact outlet, and the same outlet's going to have the same exact voltage in either case. And so if it has the same voltage, the one that's going to have a greater current is going to have a greater power. And by increasing the resistance, you're going to decrease the current. Okay, and so you can think of, okay, the one that has a greater power usage has the greater amount of current, which must have a smaller amount of resistance. And so 100 watts has a smaller resistance. Okay, so that's that. So we might have some of these kind of conceptual questions. I mean, if you call it a conceptual question like that, right? You know, say, okay, this one has less resistance, but there's nothing going to be any real conceptual stuff on the test. It's going to be all problems like this. So we're all done. This is it. Last class of the year. And tomorrow we got our test. And then after that, it's all done. We're all done. Any questions? Should that have been ohms? Where? Resistance. Yeah. You mean this one? This is ohms. Or maybe I read this a long time ago. Maybe I just forgot to read it. You mean up here? And then that whole confusion? Okay. Anyway, no, the last problem. Wow, I can't believe, yeah, I know. The last problem, where should the ohms be? I mean, I think we do have ohms right there, right? 1,100 ohms there. I think all the units are right. I'm not sure. Number 6. Oh, you mean the last problem, not the last problem, but the previous problem. Okay, yeah. And I think we worked that out, right? Yeah, okay, good. Any other questions? All right, oh, you guys I can't believe this. I got so mad yesterday. I mean, I was already, kind of disappointed about what's going on in the world in general. But you know what else happened? A groundhog ate almost my entire garden. Like it just went and took my peas. So I got some snow peas, and it just ate them all off from the bottom. It was just chomped away at them all. And then it ate all the leaves off of my zucchini plants. It didn't mess with my tomato plants, so they're still alive. But it just destroyed half of my garden. I was so sad. And I was thinking, what should I do? And so, we'll see if it survives. But I was going to maybe build a fence around it. But I was thinking a fence would be so expensive to build, and you got to have you got to have a whole, door and all this like posts and all that stuff. It's going to be over $100 just to put a little fence for garden. What's the point? And so I made up some hot pepper spray, because I eat a lot of hot sauce and hot spicy things. And I figured groundhogs don't like that. I'm not going to make poison because I don't want a dead groundhog, and I don't want poison on my plants. But I think they probably don't like pepper spray, right? And so, yeah, and I'm not smoking milk because I don't know where he lives. I think he lives on my neighbor's property, not on my property. But he comes over to my property to eat my stuff. But I'm thinking that pepper spray might actually work, right? As soon as he takes a bite, those groundhogs don't like spicy food, right? I'm thinking that they don't. And I have some pretty spicy pepper spray here. So we'll see, but I think he totally killed my snow peas, which I'm like really sad about. But anyway, it is what it is. Yeah. Yeah, I don't know. It's grab the pitchforks. Yeah, I think those little guys are faster than me. As soon as I get outside, those things are going to be gone. So, and I'd rather not have the blood of a groundhog on my head. I'd rather just make them gasp because they've bit something super spicy. So that's my plan, and I think it's going to work. Anyway, cross country. All right, cool. So see you guys. That's how we're gonna end the year. Talking about my garden and my love for spicy food. And hopefully see you guys next year. There's all kinds of plans. Who knows what's actually going to happen? We'll see. But good luck for tomorrow. Glad that you guys stuck around and that it wasn't just me talking to nobody. That's fun. And glad that you guys were checking my answers, because I got to be honest, I did not solve these problems ahead of time, and you guys caught my wrong answer. So thank you for your participation. And it's been a pleasure teaching you guys. You guys are awesome. I've taught you guys for a couple years now. And yeah, you guys are awesome. So thank you. And I'm going to go ahead and sign out. See you guys tomorrow. All free response. All right. See ya. And God bless.